We will start our lectures. Our topic today is Introduction to Medical Image Analysis and Processing. In the few group, we got chance have these lectures, have this practical class, and some general understanding about medical image analysis and processing you got. What question we will discuss today? Imaging and medical science, medical images occlusion, analysis and processing, PACS and DCOMS. Imaging in medical science. These multidisciplinary fields, medical image and image analysis, medical image modalities, and medical image information. Imaging is an essential aspect of medical science for visualization of anatomical structure and functional or metabolic information of the human body. Also used for structural and functional imaging of human body is important for understanding the human body anatomy, physiological process, function of organs, behavior of whole or part of organs under the influence of abnormal physiological condition or disease. A multidisciplinary fields we will discuss few. Medical imaging in diagnostics, radiology has evolved as a result of the significant contribution of a number of different disciplines from basic science, engineering, and medicine. Now we discuss about for what direction, what specialty I include for create medical image, for example, in the radiology, and who connect in the development these methods, connect medicine, scientists, engineering, and of course, future users, which will use, interpret, and do medical different solution, creates different medical trajectory on the basis of this medical imaging. For radiology, a number of computer vision methods have been developed for a variety of applications in the image process, segmentation, analysis, and recognition. However, computers' image reconstruction, processing, and analysis methods have been developed from medical imaging application, require specialized knowledge of a specific medical imaging modality that is used to acquire images. The application domain knowledge has been used in developing PIN models for accurate analysis and interpretation. Different fields which can use medical image, this physiology and current understanding, physics of imaging, application and intervention, instrumentation and image occlusion, and computer processing, analysis and modeling. A collaborative multidisciplinary paradigm of medical image research and applications. The development of imaging instrumentation has inspired the evolution of new computerized image reconstruction, process and analysis methods for better understanding and interpretation of medical image. The image processing and analysis methods have been used to help physicians to make important medical decisions through physician-computer interpretation. Recently, intelligent or model-based quantitative image analysis approaches have been explored for computer-aided diagnosis to improve the sensitivity and specificity of radiological tests involve medical image. Medical image can use are present in the radiological science in the last 2 decades have witnessed a revolutionary progress in medical image and computerized medical image processing. Advances in multidimensional medical image modalities, X-ray mammography, X-ray computer tomography, single photon computer tomography, positron emission tomography, ultrasound, magnetic resonance imaging, functional magnetic resonance imaging. Important radiological tools is diagnosis and treatment, evaluation and intervention of critical disease for significant improvement in the healthcare. Medical image modalities are present energy source for image, and we can classify by direction external, internal, and combination external and internal. For example, external we use for X-ray radiographs, X-ray mammography, computer tomography, ultrasound, optical transmission, and transillumination imaging. In this case, we have outside source or X-ray or ultrasound, and we see how body interact with this external radiation, this external energy. Internal, this is the result nuclear medicine, positron emission, and tomography. In this case, we have internal activity and only a present registration. And combination external and internal, we have some magnetic, optical, or electrical influence, and we see internal reaction for this, and this internal reaction we sense and analyze. The objective of medical image modalities. The objective of medical imaging is to acquire useful information about the physiological process, organs of the body by using external or internal sources. We will continue internal nuclear medicine imaging use and internal energy source through an emission process to image the human body. Radioactive pharmaceuticals are injected into the body to interact with selected body matter or tissue to form an internal source of radioactive energy that is used for imaging. For example, single photon emission computer tomography. For external, its anatomical imaging are based on the attenuation coefficient of radiation passing through the body. X-ray, radiographs, and computer tomography. And next, MRI. Combination use external magnetic energy to stimulate selected atomic nucleus. The excited nucleus becomes the internal source of energy to provide electromagnetic signal for imaging through the process of relaxation. Electromagnetic radiation spectrum you can find there from all line which we use from 10 power 3 wavelengths to the 10 minus 14 wavelengths meter, this in the hertz, and energy in the electron volts. In this case, we can find a range of energy which we can use. As you know, we can use, we can listen frequency, for example, from 10 to 20,000 hertz. For example, this we can hear it. For example, wave for MRI, we use in this from like 10 to 10 minus 1 frequency. X-ray also you can find only small range which are using. Another range we don't know what is going there, not usable for people now. Medical information. Medical imaging information. For example, for study anatomy, use X-ray radiography, X-ray computer tomography, magnetic resonance, ultrasound, and optical methods for study anatomical structure. For study functional metabolic is spectral analysis, PET. All this all this equipment also use an ultrasound, optical fluorescence, and electrical impedance. Medical images occlusion, analysis and processing. Medical. Dear student, can you off your camera? Dear student, off camera, off microphone. Biomedical images processing and analysis system, digital image concepts, transmission imaging, medical image analysis and processing. In this chapter, we will discuss about this. Biomedical image processing and analysis system. General purpose biomedical image processing and image analysis system must have three basic components.
Join the current.
We will continue. Biomedical image processing and analysis system. A general purpose of biomedical image processing and image analysis system must have three basic components. Image occlusion system usually converts a biomedical signals or radiation carrying the information of interest to digital image. Digital computer system unit, usually large memory units that are used to store digital image for further processing. Image display environment. The output image can be viewed after the required processing. Yes, these steps are important. Yes, for begin, how this works in general scheme of biomedical image analysis system. Yes, we have scanner and we have some object. We collect image occlusion system. Are present digital computer and image processing unit. And after that, we can display our result. What is image? Image, as you know, your screen, mobile, or anyone consists of from pixel, picture element. And often you listen about the amount of pixels which are present in your screen. And we can identify, and each pixel have some coordinate f, x, and y. Also a present intensity value at xy. This can be grayscale or this can be color scale, different variants present. Image is a two-dimensional signals. The value xy at any point is gives the pixel value at the point of an image. Pixels, picture size, resolution can be different. You can find different. And not included there also. And coordinate, gray level or 8-bit pixel or another way will be present in the coordinate fxy. This means each dot will have some location and some value of gray level or color level. Digital image information. Initially, like you have some tissue organs, and in the result, you will get like this digital image. This means if you have volume object, so often quality and effectiveness processing of images can can miss some part of information. You see, for example, each pixel will have some color and grayscale or some coordinate. In this case, few information can be missed from original object. Continuous image projects into a sensor array, result of image sampling and quantization. For example, you can find how will analog and digital signals. This will be blue one, this analog. And digital signals, this will be value of grayscale digital samples in the all matrix. For example, you can see digital sampling and pixel quantization. Yes, each pixel have different value. This means different color code will be present there. And in this way, you can find some images. This we discuss about principle. Now you can find characteristics area xy, which, for example, x is wave axis x and axis y, and for each point you can identify location, and also you can identify also some additional value, or for example color or grayscale value, or any another information additional. Transmitting mission imaging. Medical image through transmission, electromagnetic radiation and imaging, X-ray imaging and radiography, computer tomography imaging in the past and current. We'll discuss now about this. Magnetic resonance image, nuclear medicine imaging, optical and emerging technology. Now we will start from first one in our list. Basic principle: radiation attenuated when passed through the body. Yes, we have transmission of energy, magnetic energy, and we have different type: X-ray radiograph, X-ray computer tomograph, infrared, optical, and microwave. Not all wavelengths in the electromagnetic radiation structure are suitable for transmission image for human body. Resolution of the desired image of human body imposes the restriction on the use of electromagnetic radiation. There are two important considerations when selecting an electromagnetic radiation for imaging human body. Resolution. For a useful image, the wavelength must be under the 1 cm. Higher wavelengths will not provide useful resolution on the image. Wavelengths should be shorter than the resolution of interest. The radiation should be reasonably attenuated when passed through human body. Too much attenuation will result in poor signal-to-noise ratio. If it is completely transmitted, it will not provide any meaningful structure detail in the image. Now we will talking about electromagnetic radiation and imaging. Wave concept of electromagnetic radiation explains why it may be reflected, diffracted, and polarized. Short electromagnetic wave, such as X-ray, may react with matter as if they were particles rather than wave. These particles are actually discrete bundles of energy. Each bundle of energy is called a quantum or a photon. Photons travel at the speed of light. The amount of energy carried by a photon depends on the frequency of the radiation. Number of vibrations per second we can calculate from this formula E, h, and nu. E is the photon energy, h is Planck constant, and nu is frequency. The particles behavior of photon leads to photoelectric effects and Compton scatter. How working X-ray? Principal X-ray was found in the 1895 and also before, where was proposed use X-ray. About this material was a present information, and only they start use for study people, body function. And in this case, are present sources where X-ray particles are leave from a filter and going through the body as there. And in the result, we can find of a bone structure and different tissue structure. How and a film provide a measure of ray attenuation in the tissue. What principle are there stored? They stored, we can see in these pictures continue. As you understand, X-ray going across of the body, and in the result of this, film or sensors identify amount of X-ray which come to the sensor. This means our body have property in absorption X-ray, and amount of energy which come after penetration body, sensors are detect. Sensors or film, this depends what digital principle or film principle of X-ray machine. As you understand, X-ray able absorb in the different tissue in the different amount. Largest amount of absorption have bone, and muscles or organs have smaller ability absorption as bone. After that, and in the result penetration are present some films or sensor which identifies this amount of X-ray which come in, and after some processing we can find X-ray. But for begin we will talking about image formation. Is a graphic representation of a cut or slice and implies the formation of 2D cross-sectional image, free of blurring from structure not in the plans of interest, the tomograms. Now we start talking about same principle which are present in the fluorography, also present in the tomography and computer tomography also. Computer tomography is the formation of tomography of X-ray absorption coefficient by the methods of reconstruction from recorded projection. The term computer tomography may be applied to any techniques that require computational in the order to reconstruct an image with non-ambiguous resolution in 3D. How working computer tomograph? In these pictures, for begin, you see how view computer tomograph in the down pictures. In the first pictures, we can find body. We can find sources which step-by-step change location, and symmetrically to this location change, sensor which identify a value of X-ray which come into the through the body, they synchronically rotate. For this gives chance for complete understand what kind of tissue and what their location are present in patient for any cross section. In the 1895, Gonsfield proposed his computer expert, and Cormac, physician, got Nobel Prize about computer tomograph. They provide 3D anatomical information, preserve topology bones, excess radiation and not good for all soft tissue. Image formation: 3 objects are viewed from a number of different angles, and then a cross-section image of it can be computer reconstructed. In the result of X-ray image found, after that mathematical result Radon transformation, and computer can, this at 1917, and computer can perform complex mathematics to the reconstruction and process imaging. This started after 1960. In the result of these skills was development computer tomograph, computerized axial tomography. Now we will try one more time discuss about principal computer tomography. For begin, we have some cross-section of body and X-ray penetrate it. In the screen, in the sensor, we have some location. And typical projection you can find like this. If we're talking about computer tomography, we have object, we have source and direction, and they constantly rotate around object, body. And in the result, they able create images from 3D analysis. And you can get by cross-section. Computer display slice views. Reconstruction cross-section. Computer tomography observe a set of projection integration along different angle of a cross-section. Each projection itself loses the resolution of inner structure, type of measurements, transmission, X-ray, emission, magnetic resonance, MRI. This working by these principles. What to recover inner structure from the projection? Emission tomography measure emitted gamma ray, but the decay of isotopes from radioactive nuclei of certain chemical components affixed to body part. MRI based on the protons possess a magnetic moment and spin in the imaging fields along two parallel or anti-parallel apply RF, allow to anti-parallel remove RF. Absorbed energy is emitted and detected by the RF detectors. Now let's see in the images. Also we have body, we have X-ray source, and we have sensor. And constantly they rotate in the 1 or 2 degree each time. For example, for very short part of seconds. And in the result of this scanning, we can get pictures, which will include different cross-section analysis. What sense radon transformation? A linear transform fxy, where present linear integral or ray zoom along a line inclined at angle from x, y axis and s away from original. Fix 0 at theta to get a 1D signal PO as G as theta. This means we can identify continue penetration from X-ray sources through body. We will get this value which will depend for amount X-ray which absorbed in the body, and we can get these pictures. Inverting a radon transformation. To recover in a structure from projection, need many projection to the better recover the inner structure. And you can find different stage of a result radon transformation and inverting. Computer tomography, as you understand, this constantly process when detectors and X-ray are rotated. Okay, we will continue. Now we go to the next slides. For only I will short explain about rotational invariance property of Fourier transformation. This way, consider a 2D constitution signals and its 2D Fourier transformation is help understand how distribute frequencies in our pictures, and in this gives chance for us understand what image consists of, and after that do construction model in this image. Maybe we not will disturb you these mathematical details. Now we will see next. Computer tomography so fast development. And for example, resolution, quality of images so fast grow. For begin, for example, computer tomography have like these images, so small quality. Original computer images have 128 to 128 resolution. And so hard something get understanding. Some later become 512 and to 512 resolution, but are present more modern solution, and you can find more better quality of imaging. For example, 5th generation of scanner use no moving part, and you with the patient inside to 110 degrees. The detector's ring is similar, and a beam scans around the body in multiply adjacent tracks to generate X-ray. Time is around 0.1 seconds to a few milliseconds or real time. As you see, this synchronically rotate as around body, and we can get image. Spiral, helical, computer tomography. Now projection occlusion process trace out a spiral trajectory, rather than a sequence or parallel. What projection funds? This is achieved by a combination of continuous beams detector rotation and continuous table movement cases the projection data to be accurate along a spiral path. It is fast. It is the X-ray computer tomography imaging system of choice for occlusion 3D volume images of many structures. Good for the application of 3D visualization and quantitative analysis techniques. Now you can find how this rotation scanning are present. You see like spiral which identify condition in the each cross section. Photo simulation of spiral computer tomography in abdomen region. A virtual reality 3D image of lungs. You can find in the result of modeling, you can find structure visualization of different tissue. Also, you can find how this visualize images in the patient. This cross section and this 3D visualization, different kind of tissue are present. Basic principle, the electromagnetic induction based on resonance function signals are collected through nuclear magnetic resonance from the excited nucleus with magnetic moment and angular movement present in the body. Most common is proton density imaging. And there you can find what step, what direction use magnetic resonance, which give chance for us get magnetic resonance structure imaging, flow imaging, chemical shift imaging, spectroscopy, and functional imaging. Yes, this so large direction are present which are using now in medicine, and this so fast development. Hydrogen nuclear proton image formation under strong magnetic fields spin in phase with one one another and allow with the fields. Relaxed protons include a measurable radio signals. And this was study from 1952. And what is plus? Priority, main modality for image guided surgery. Superb ability to discriminate between subtle difference in tissue characteristics, very safe, and less accurate for bone scanning. For example, MRI. MRI better for computer tomography. And now we can see how this can go in. We have platform for patient which come inside, are present gradient coil, RF coil, and gradient coil also there present, and magnet. From this data occlusion system, monitor and computer help illustrate, visualize data processing result. You can find how we'll view MRI scans of head. You see this so detailed scan of cross-section head. MRI modalities. There are several imaging modalities within MRI Expert 41 and 42. MRA can use for magnetic resonance angiography image of vessels. MRS for spectroscopy, images of chemistry of the brain and muscle metabolism. Functional magnetic resonance imaging of brain function. Perfusion weight imaging. Diffusion weight imaging MRI, and images of nerve pathway. Magnetic resonance angiography. Scanner tended to measure only moving structure. This only blood, no static structure. Generates 3D images of vascular system and may be enhances with contrast agent. This we talk about angiography. Functional MRI. This gives chance study about active brain regions demand more fuel, oxygen. Extra oxygen in the blood changed MRI signals. Activate brain region with specific task. Oxygenation blood generated smaller 1% signal change. Correlate signal intensity change with task. Represent changes on anatomical images. Continue. This can for more detailed understanding functioning of brain are using different experiments. For example, subject looked at flashing disk while being scanned, and activated sites detects and merge with 3D MRI image. You see we show for person different kind of stimulus, and we can understand what is part of brain become active. MRI advantage. The most important advantage of the MRI is its ability to provide unprecedented contrasts between various organs and tissues and the three-dimensional nature of imaging methods. Selective 3D imaging is provided by appropriate selection of gradient fields and phase encoding methods. A variety of contrast image can be created by different combination of weighting of T1, T2, and echo images. MR spectroscopy provides a great potential for meaningful tissue characteristics. Functional MRI holds great promise for the future. Nuclear medicine imaging. Nuclear medicine imaging system image the distribution of radioisotopes distributed with the body, preferable to a specific organ or structure of interest. It provides a direct representation of metabolism of or function in the organs or structure being imaged. Two main technologies: single photon emission computed tomography and positron emission tomography also present. Single photon emission computed tomography, the systems image the distribution of radiopharmaceutical, then emit photons upon decay using gamma camera. Image reconstruction is similar to X-ray computed tomography. Patient will be injected or inhaled a small amount of physiologic radioisotope tracers. Its principal strength is ability to provide functional information by the use of radiopharmaceutical that are indicator of in vivo biochemical or hemodynamic function. Now we can find illustration for single photon emission computed tomography, where present organ with radioactive emissions, and we have detection crystal, we have photons tube array, positron logistic criteria, and detector cover, and this go into computer. Positron emission tomography produce transverse tomographic image of the distribution of positron emitted radionuclides systematically administered to the subject under study. The image data is supplied by the detection on the annihilation radiation emitted as a result of the annihilation of positron in matter. Radionuclides commonly used are carbon-11, nitrogen-13, oxygen-15, and another. Positron emission tomography is very useful in the study of biochemical process of fundamental importance in biology and medicine. You can find some illustration of positron emission tomography. Detection of radiation from the emission of positron. This was development in the 1998-2001. Two doctors which you can find there, and they development what is positive, valuable techniques for some disease and disorders. Amount of radiation is smaller and invasive inject radioactive material inside of tissue using in the positron emission tomography. Like these images possible get in the result using positron emission tomography. For example, this will be view. Now we compare different kind of images. MRI and positron emission tomography, it's comparing. And also possible do combination of this imaging and also this result as well. Ultrasound imaging. Basic principle back scattered echo and Doppler shift principles are more commonly used with the interaction of sound wave with human tissue. Sometimes the scattering information is complemented with transmission or attenuation related information such as velocity in the tissue. We have acoustic energy, we have ultrasound transmission or ultrasound echo. Acoustic absorbed, blockers, piezoelectric crystals, image object. And in the result, maybe there, oh yes, this we will discuss now. Now we have pulse generator and timing, transmitter receiver circuit, control circuit, data acquisition analog to digital converter, computer image storage and processing, and you have display. How this will working? We have ultrasound which generate pulsation to the tissue, and dependently frequency of these sources, ultrasound, different tissue can reflect it. And in the result, we can know about what tissue and form and area of this tissue are present there. For thicker part of the body, such as abdominal imaging, frequency is about from 1 to 3 MHz, are used to provide reasonable attenuation. Unlike X-ray, in ultrasound image, the image are produced through a reflection or echo using the known velocity of propagation to calculate the depth. In the ultrasound imaging, are cases excessive attenuation and therefore cannot be used to study some anatomical structures such as lungs. Ultrasound imaging operated close to the diffraction limits because of its larger wavelengths compared to X-ray. Now in these pictures you can find different kind of ultrasound. For example, this 2D, 3D, and 4D. This means in time dynamical process available. This non-invasive nature and capability of providing excellent information for objects immersed in fluids. Low velocity of propagation as compared to the free space velocity of X-ray, which is 3 by 10⁸ meters per second. This makes the time of flight measurement possible using ultrasound with pulse echo techniques. Unlike X-ray, the velocity of propagation of ultrasound is dependent on the material. Ultrasound provides a variety of reflective indices of materials, Thus, selective imaging of specific plants is feasible with ultrasound through the construction of so-called lens system to provide image of focus structure. Optical imaging. Basic principle. Optical photons are transmitted into the tissue for transillumination. As a result of photon cells, interaction, diffusion of photons result in forward and backward scattering and absorption. The backscattering scattered light photons are recovered as remittance to provide data for imaging. Examples include nevoscopy and breast imaging through transillumination. And this present in the optical image view direction. Transillumination, diffusion tomography, photon migration tomography, optical imaging. The imaging resolution is not as good as X-ray, but for certain kind of non-invasive images, it's sufficient to provide meaningful information. Examples include endoscopic and nevoscopic imaging. Infrared imaging specifically provide additional information about temperature of the object because of its smaller photon energy. Ultraviolet rays, along with the dews, are used for fluorescence imaging. The dew absorbed by the tissue case, the tissue or cells to absorb ultraviolet radiation, resulting in the emission of electromagnetic radiation in visible range to form the image. Nevoscopy, imaging by transillumination. Optical image technology for imaging skin lesion, non-invasive, cost-effective, easy to use for screening light complete visible or narrow band spectrum, penetrates skin area around the lesion. Back-scattered light re-emerge from the skin forming image of the transilluminated skin lesion. Images of skin lesion can be captured through rotable optical mirror geometry from different angles. Images are treated as 2D projection or 3D transilluminated lesion for 3D reconstruction using photon diffusion model and interactive reconstruction algorithm. Now you can find how this working there. We have a lens system and we have skin. We have nevoscope provides both transillumination and self-illumination, and any regulated combination of these two illumination methods are present. And you can find how this will be a result of nevoscopy. Now we will talking about basic medical image processing. In this part are present digitalized processing. For beginning is occlusion and visualization, but between this is processing. And in our classes we will try get some few experience about processing imaging. pre-processing, segmentation, detection, analysis, and diagnostics. Scheme of image processing are present there. Are present occlusion, digitalization, are present calibration, optimization, transformation, registration, and filtering. And in this range are present in the visualization stage, SUV, Keresons, construction, illumination, shading, and display. In the analysis are present segmentation, classification, interpretation, and measurement. And in this management is compression, achieving, retrieval, and communication. What stage for pre-processing of image present? For begin filtering, image denoising, image registration, and image enhancement. List of algorithms for pre-processing you can find there. Median filter, mean filter, wavelet-based denoising, and wavelet-based image registration. Now we will see different kind of filtration. Gray level resolution, and we can find different spectra, different amount grayscale. This resolution will be best because amount of grayscale part will be is greater in this first one. And this only binary, black and white. And we will see this also in the classes hour. Image processing task, future enhancements. This you have image through future adaptive contrast enhancement algorithm are present there study because you see more active contrast liquid substance are present there. Segmentation exactly delimitate objects once they are detected. Vessels, liver, cardiac image, left ventricle, brain. We can find different way and result visualization. You see we get image and we can create some visualization like this or this right image also. This will be liver and I think this lungs. A list of segmentation algorithm you can find there. This Kamin, fuzzy, narrow fuzzy, neural network based segmentation, snake algorithm, and Searle-Holding based segmentation. And you can find how will view imaging after segmentation. You can find different one pictures. Detection. Found location of object of interest without prior knowledge about their local existence. Bones, organs, polyps in colon, and nodules in lungs. Computer tomography chest imaging. Yes, you can find how the civil can found in detail cross-section, one of chest cross-section. Medical image fusion. You can find how this will be viewed. Multiply modality images are registered and overlaid or merged to provide additional information. This you can find different recurrent malignant disease from therapy include changes, MRI and photon electron tomography. You can find diabetic retinopathy ultrasound imaging, at least one microaneurysm, earliest clinical detectable lesion, retinal hemorrhage, hard or soft exudates are possible found there. Macula, optic disc, hemorrhage, and aneurysm you can find there. This we can know about ultrasound diagnostics of eyes. Paradigm of medical image processing. To begin with image formation digital, pixel data manipulation, visualization, print and display and storage and transfer. After that, this passed acceleration rapidly. After that, evolution, formation, image, registration, segmentation, and classification. In the future, standardization, usability, are present image formation, multidisciplinary, diagnostics, intervention, planning, and treatment. Now we will talk about different formats storage of data. We will talking today about two formats, PACS and DCOMS, picture achieving and communication system, digital imaging and communication in medicine. Picture achieving and communication system in medicine, image, picture achieving and communication system PACS. A computer or network dedicates to the storage, retrieval, distribution, and presentation of images. The most common format for image storage is DCOM, digital image and communication in medicine. Picture achieving and communication system use. Replace hard copy based means of managing medical images such as films, archives. It expands on the possibilities of such conventional system by providing capabilities of sites viewing and reporting, distance education and telediagnostics. Additionally, it enables practitioners at various physical locations to access the same information simultaneously, provide a single point of access for image and the associated data. It should also interface with existing hospital information system. Picture achieving and communication system architecture. Typically, a PACS network consists of a central server that stored a database containing the image connected to one or more clients via a LAN or a WAN, which provide or utilize the images. Web-based picture achieving and communication system is becoming more and more common. This system utilizes the internet as their means of communication, usually via a virtual private network or secure sockets layer, as software, thin or smart clients. Smart clients is loaded via ActiveX Java Net framework. Client workstation can use local peripheral for scanning image films into the system, printing image films from the system, and interactive display. PAX-IM. This can use DCOM image for different kind of users, which we can get from occlusion modality, from different kind equipment, for analysis, and for visualization for different users. Also, there can be different kind of storage system and a different kind of users. There are present physicians, patients, and different and other doctors are present there. Continue. Now our lectures will complete, will finish. Does you have any question? Okay.
No,
Thank
sir.
you.
No, sir.
I wish good luck for you. Thank you for your attention. Bye.